In this lesson, we're going to talk about organic chemistry. When we talk about organic chemistry, we're dealing with the chemistry of carbon-containing compounds. And when we deal with carbon-containing compounds, they're also called hydrocarbons. And when we look at that name, it actually tells us that it has carbon atoms and hydrogen atoms in them. So all organic compounds contain carbon and hydrogen. So we want to talk a little bit about carbon atoms as a review. And if we look on the periodic table, we can see that carbon has 4 valence electrons. That means that it tends to make 4 very strong bonds with other atoms. And in organic chemistry, what we notice is that carbon atoms tend to bond to other carbon atoms to form long chains and elaborate rings. And the structure of organic compounds is directly related to the function of those compounds. Now, there are 2 things that we're going to deal with when we talk about our organic chemistry. First is what we call our chemical formula. And a chemical formula is a formula that tells us what types of atoms are present in the compound and in what ratios. So if we look at water as an example, water has the chemical formula H2O. Which means it contains hydrogen atoms and oxygen atoms, and the ratio is 2 hydrogen atoms for every 1 oxygen atom. And if we were to look at glucose, its chemical formula is C6H12O6, which means that glucose contains carbon, hydrogen, and oxygen, and the ratio per molecule of glucose is 6 carbons, 12 hydrogens, and 6 oxygens. Now, the other thing we're going to deal with in our organic chemistry chapter is what's called a structural formula. And what the structural formula does is it tells us how the atoms in that particular molecule are arranged. So today we're going to talk about a couple of different types of simpler organic compounds. And our first one is what we call our alkane series. And when we look at the alkane series, they're considered to be saturated hydrocarbons. They contain carbon and hydrogen, and the bonds between the carbon atoms are all single bonds. Now, when we look at the formula for all alkanes, they follow this general formula, CnH2n plus 2. That means that for every n number of carbons, we have 2n plus 2 hydrogens. So if n equals 1, we would have 1 carbon, and we would have 2 times 1 plus 2, or 4 hydrogens. If n equals 5, we would have 5 carbons, and 2 times 5 plus 2, or 12 hydrogens. All alkanes are considered to be saturated hydrocarbons because they only contain single bonds. When we name alkanes, the suffix that's used is ane. And when we look at the name alkane, it also contains the suffix ane. And oftentimes the suffix for a name of an organic compound gives us an indication as to what kind of organic compound it is. Now, we need to talk about prefixes in organic compounds because the prefixes give us an indication about how many carbon atoms there are in the particular structure. So we're going to go through a series of prefixes that we're going to use throughout the chapter. So our first prefix is meth, and that prefix indicates that we have 1 carbon atom. Eth refers to 2 carbon atoms. Prop is 3 carbon atoms. Bute is the prefix for 4 carbon atoms. Pent is 5. Hex is 6. Hept is 7. Oct is 8. Non is 9. And dec is the prefix we use for 10 carbons. Now, there are prefixes that go beyond 10 carbons, but for what we're going to do, we only need to know these. So now we're going to look at a couple of examples, and we're going to look at the chemical and structural formulas. Our first example is going to be methane. So we need to think about what the prefix meth means. How many carbons does the prefix meth refer to? Okay, 1. And since it's got the suffix ane, it's an alkane. Alkanes have the formula CnH2n plus 2, so our formula for methane will be CH4, and that would be considered your chemical formula. Now the structural formula is going to show us the way that those atoms are arranged. And we draw our carbon atoms first, and then put the hydrogen atoms around the carbon atoms. And we always have to remember that carbon forms 4 bonds, whereas hydrogen atoms form 1 bond. So when we look at the structural formula for methane, we've got our central carbon, and then we've got 4 bonds between that carbon and each of the hydrogens. So another example would be propane. Okay, so we look back and find out what the prefix prop stands for. All right, so that stands for 3 carbons, so N equals 3. Our formula for alkanes is CnH2n plus 2. So the formula for propane would be C3H8. So when we go to write the structural formula, we'll start with our carbons, and we'll put single bonds between each of the carbon atoms since it's an alkane, and alkanes are saturated hydrocarbons. And then we'll fill in each of the carbons so that they have 4 bonds each with hydrogens. Now what I did here is kind of a shortcut or a skeletal structure. I've got 1, 2, 3 carbons. Each carbon needs 4 bonds. So this carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. And this carbon has 1, 2, 3, 4. Now here are hydrogens. But what I'm going to do to kind of shorthand this structural formula is I'm going to leave the hydrogens off. We're going to assume that they're there. We kind of know in our head that they're there, but we're going to write them kind of shorthand to make things easier. So now we're going to look at pentane. And when we look at pent, what number of carbons does pent stand for? Okay, so 5. So N equals 5. We plug that into our formula for alkanes, and we get C5H12. So we'll put all of our carbons along in a chain. Since it's an alkane, we'll have single bonds between the carbons, and then we'll saturate them with hydrogens. So 1, 2, 3, 4, 5 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And there's the structural formula for pentane. Now the next thing we want to talk about is the fact that alkanes are not usually just one long chain of carbons, but oftentimes there are lots of branches coming off of the carbon atoms. So we're going to go through the rules on how to name branched alkanes. The first thing we have to do is we have to decide what the longest continuous chain of carbon atoms is. And sometimes that's straight across, sometimes it might zigzag through the molecule. And that longest chain is referred to as our parent chain. And we would use the prefixes to stand for how many carbons are in that longest chain or that parent chain. Next, we would number the carbon atoms, starting from the end closest to the first branch. Then we're going to decide how many carbon atoms are in the branch, use our prefixes, and this time the suffix for our branch is YL. Like if it's a methyl group, it's a branch with 1 carbon. Or if it's a butyl group, it's a branch with 4 carbons. Now, if there's more than one of the same kind of branch, then we're going to use prefixes like di and tri. So if there were 2 ethyl groups, we would refer to it as diethyl. Or if there were 3 methyl groups, we would call it trimethyl. If there's more than one kind of branch, they're listed in the name alphabetically. So let's look at a couple of examples of branched alkanes. Okay, the first one we'll look at is 2-methyl pentane. And really what you want to do is start from the end of the word and work towards the front of the word. So the suffix ane tells us we only have single bonds, or it's a saturated hydrocarbon. Pent tells us that we've got 5 carbon atoms in our branch, or in our parent. So we've got 1, 2, 3, 4, 5 carbons in our parent. Then we've got that YL suffix, which tells us that there's a branch. The meth tells us that there's 1 carbon in that branch. And the 2 in front tells us which carbon that methyl group is coming off of our pentane parent. So we're going to start numbering our carbons 1, 2, and off that second carbon, we're going to put a methyl group. So that would be 2-methylpentane. So let's look at another example. Let's say we've got 2,2-dimethylhexane. So we've got a saturated hydrocarbon, so single bonds between the carbons. We've got 6 carbons in the parent. So 1, 2, 3, 4, 5, 6. We've got branches. The branches are methyl branches, so they each contain 1 carbon, and there are 2 methyl branches. The numbers tell us where those branches are coming from. So we're going to have a methyl group coming off of the second carbon, and we're going to have a second methyl group coming off of the second carbon. And again, remember that we would fill in all of these spaces with hydrogens. For simplicity, though, we're just going to do the skeletal structure. So let's say we've got 2,4-dimethylhexane. So again, we start from the back. We've got single bonds between our carbons, 6 carbons in our parent chain, so there's our parent. We've got branches, 1 carbon in each branch, and there are 2 branches. The difference this time is where those branches are. One's off of the second carbon, and one's off of the 4th carbon. So that's 2,4-dimethylhexane. So let's look at this one. A little bit longer name, but we can just break it down. Single bonds between the carbons, 7 carbons in our parent. So there's our parent, 1, 2, 3, 4, 5, 6, 7. We've got branches. 2 of the branches contain 1 carbon, and they're off of the second and the 5th carbon on the parent. And 1 of the branches is an ethyl group, so it's got 2 carbons, and it's coming off of the 3rd carbon of the parent. So we'll start with the methyl branch. We'll count over 3 carbons, 1, 2, 3, and we'll put that ethyl group. Then we'll count over 2 carbons, and we'll put our methyl group. And then we'll count over 5 carbons, 1, 2, 3, 4, 5, and we'll put our other methyl group. Now notice that ethyl and methyl are alphabetical. Even though the methyl group came first, we're going to name the ethyl group first because alphabetically that's the way we do that. So that's our introduction to organic compounds. You have an assignment that you need to work on with organic compounds, so get working on that, and we'll see you next time.